welcome to another episode of Inside the Sciences. I am your host, Sheena Verhal. And you see, every day in hospitals and pharmacies, healthcare professionals perform a delicate balancing act. They are tasked with the creation of life-saving treatments, but they're simultaneously navigating invisible dangers that might actually threaten the products, the patients, and themselves. That is why in this episode, we are pulling the curtain back on those dangers and on the advanced technology that is designed to manage them. And joining us today is Handini Setiwati, a product management executive here at Esco, to walk us through compounding isolators. Hello, Handini. Welcome to Inside the Sciences.
Hi everyone, my name is Handini. I'm a product management here at Esco.
All right, so we're going to talk about compounding isolators today with Handini. All right, so we can start with, we have high stakes reality when it comes to compounding. So, for example, let's talk about a common scenario. For example, there is a pharmacist and that pharmacist is preparing a total parenteral nutrition or the TPN. So, from the moment they open, say, a vial, what is the invisible enemy that they're actually fighting against, and what's the worst case scenario that that may happen if they lose the fight?
Okay, so the pharmacist is fighting against microorganisms and also particles. So every movement from wiping down the vial to injecting the nutrient into the TPN bag is a step to keep these germs getting into the medication. Not only the germs, but also the particle as well. And if a few of those contaminants get into the IV fluid, it can cause contaminated medication. When we injected the medication into patient bloodstream, for example, then it can cause a severe blood infection and potentially it can damage a patient organs, and in the worst cases, it can lead to death.
That is it's a very scary thing to happen. Now, how about when we talk about, high risk drug like chemotherapy? Now, what exactly are the pharmacists being exposed to, and what does the research tell us about the real health impacts like organ toxicity or even cancer risk for staff who are exposed, particularly those staff that are exposed repeatedly?
Okay, so when we are handling hazardous drugs like chemotherapy, there is an exposure risk for operator, and it can come from aerosols and also from fine powders and liquids they handle. And it can enter the body through for example, like ingestion, inhalation, and body absorption. And research has shown that exposure to these drugs is linked to organ toxicity, specifically for our liver and also kidney. There's also a significant risk of cancer, like leukemia and other blood cancer. For this reason, containment is non-negotiable. It's not just about patient safety, but also it's protecting the healthcare professionals.
Yeah, okay. Those are really scary things to happen. And the thing is, they are not theoretical dangers. They actually could happen in real setting, right? So, if speaking of these dangers, are there actually regulations that are related to compounding practices?
Okay, there are several regulations that we need to know. If you are compounding, for example, like non-sterile, non-hazardous, then you follow USP 795. This regulation is focused to make sure that the product is accurate and safety for the patient. So you don't have to need clean rooms or heavy containment. So you just need to perform a good compounding practices. And if you are preparing for sterile, non-hazardous drugs, then you can follow USP 797. The regulation here is to manage, to protect the product and the patient. It means you need to perform aseptic technique, clean room standards and control environment should be maintained to keep contamination out. And the other regulation that we need to know is USP 800. So when you are handling hazardous drugs, whether it's sterile or non-sterile, then you can follow this regulation. The purpose of this regulation is to protect the operator and the environment. So you need to have containment cabinets or isolator, and also negative pressure inside the rooms and PPE. So in short, for non-sterile drugs, it's USP 795, and for sterile and non-hazardous, it's USP 797, and for hazardous, it's USP 800.
All right. Those are actually very good regulations that we could remember. So you guys take note of those regulations. Now, let's move forward with, since we're talking about regulation. So how do these regulations basically set environmental conditions that would protect the operators and the products themselves?
Okay. This regulation manage environmental condition to protect the product and prevent the exposure of the chemical into the operator. So there are several terms that we need to understand. And the first one is primary engineering control, or PEC. We call it a PEC. It's equipment like lab, BSC, isolator, where the pharmacist performing compounding practices. So for this one, depending on the drug being handled, they need to meet a certain degree of air cleanliness.
Yeah.
For sterile preparation, both USP 797 and USP 800 states that the PEC must provide at least ISO class 5 air quality.
Okay.
So what is ISO class 5 air quality, right? Yeah. For every particle with size of 0.5 micrometer, the number of particles should not be more than 3,520 particles per cubic meters. And for USP 797, the pressure of the PEC should be positive, and for the USP 800, it should be negative relative to the secondary engineering control, or SEC. So the next question will be, what is SEC?
Exactly. Yeah.
SEC is a clean buffer room where the air quality inside must be at least ISO class 7, with a maximum of particle around 352,000 particles per cubic meter, with a size of particles 0.5 micrometer. This room has a positive pressure for USP 797 and negative pressure for USP 800 relative to the anteroom. When a full clean buffer room is not possible, then you can place the PEC in the segregated compounding area, or SCA. SCA SCA doesn't have to meet the same strict requirement like a clean room, but it doesn't mean that it's a free pass. It still needs to comply with requirement like air change per hour and also room pressurization. And it becomes critical when we're talking about hazardous sterile preparation.
Yeah.
You need to have negative pressure and sufficient air exchange to keep both the product and the operator safe.
All right. So that's actually a very comprehensive, what the answer about, the regulations when it comes to environmental conditions, right? All right. So let's move forward with the core technology, because you've been mentioning negative pressure and then positive pressure. And I understand that that's the principle behind isolators, right? We have the pressure control. So now, can you explain, like perhaps using a simple analogy, how positive pressure creates like a safe zone for, particularly when you're working with non-hazardous products?
Okay. For an isolator with positive pressure, the pressure inside the chamber is higher compared to the pressure in the environment or the room. The outward flow will be continuously forced out, which create a protective barrier, preventing external contaminants from entering the chamber. Analogically, it looks like blowing up a balloon. The balloon's interior represents the safe zone for a product. The air pressure inside the balloon is slightly higher compared to the environment. When you poke a tiny pinprick hole in the balloon, instead of room air rush in, the air inside the balloon will rush out, right? Yeah. It's the same way with a positive pressure isolator. The fan of this isolator will continuously clean filter air into the chamber. If there is a minor leak or glove port is open, the higher pressure inside ensures that clean air always flows out. So this outward flow pushes any contaminants, creating a protective barrier around the product.
Okay. That's actually a very good analogy because I understand it now, how positive pressure really works. Now that we know, and I hope that you understand because it's really good analogy with the balloon that Handini talked about. Now we also have the negative pressure. So how does a negative pressure work? Specifically, I think it's like a containment field, particularly to protect the operator from hazardous powders and vapors. So how does this pressure work?
Okay. The negative pressure basically is the opposite of the positive pressure. It works by creating a lower pressure inside the chamber compared to the pressure in the surrounding area. It looks like a vacuum cleaner. The vacuum hose and the dust bag represent the isolator. When the vacuum's motor will create suction, which means the pressure inside the vacuum is lower than the pressure in the room. So when you turn on the vacuum and then you put the hose near a mass, the higher pressure in the room will rush into the hose, right? Bringing all the dust with it. It's the same way with the isolator with negative pressure. When the door opens, air from the door from the room, it will flows in, preventing any infectious agents or hazardous drugs from escaping into the non-contaminated area. But when it comes to hazardous drugs, it will be maybe slightly easy for powder can be captured because there is an filter, but it will be different for a vapor. When you are working with volatile substance like a vapor, it's mandatory to connect the isolator to an external exhaust duct. This prevents vapor buildup inside the work zone. And some isolator can be fitted with carbon filter. The function of carbon filter here is to reduce the risk by absorbing certain vapors. But it should be noted, even with carbon filters, venting the isolator to the external is mandatory, especially if the product is volatile at the room temperature.
Okay, another great analogy with you're great with analogies because I also understand this how negative pressure work. It's like a vacuum. Okay, so let's dive into the models that we have here, in Esco particularly. So we have what we call the closed restricted access barrier system, right? The RABS. So can you tell us how does the streamlined RABS fit into the ecosystem and what are the typical, say, scenarios where a customer might choose a RABS?
Okay. So SLC RABS so basically SLC RABS is a restricted access barrier system. When we back to USP 797, it states that RABS is an enclosure with ISO class 5 air quality. So this system allows for entering and removing material through defined openings. In contrast to laminar flow air clean benches or biological safety cabinets or BSC, RABS provides more sterility assurance to prevent the risk of contamination due to the additional physical barrier of the RABS itself.
All right. So in relation to that, can you tell us what is the difference between SLC RABS and an isolator?
Okay, so SLC RABS is not pressure tested like Isolator. So we can say that its containment capability is not as strong as Isolator. In the Isolator, we perform pressure tested to make specific containment class standards. But we need to know that according to USP 800, SLC RABS can still be used for handling hazardous sterile preparation as long as the SLC RABS is externally vented. And if we look at the design of the SLC RABS, it typically runs in recirculating airflow mode with simpler controls and fewer features. It makes the SLC RABS more cost-effective solution for compounding practices, especially when the budget are tight. And for Isolator, it offers a lot more flexibility. It can be pressure tested, and for the airflow configuration, you can choose the option not only just recirculating. And it has a wide range of features that add value for the isolator itself. So it makes isolator more suitable, not just for pharmacy compounding, but also for a broader application in pharmaceutical manufacturing.
All right. Okay. You mentioned earlier about pressure tested. So when we say pressure test, can you tell us specifically here in Esco, how do we do that? How do we pressure test?
Okay, so in ESCO, we perform pressure tests to check air leak tightness inside the isolator, which is regulated in the ISO 10648-2. We first supply pressure inside the chamber to a set level. Then we monitor the pressure decay over time. The slower the pressure drops, the more airtight the isolator is. If the test is performed manually, the technician should check the pressure gauge over time. However, if the requirement for a pressure test to be conducted in daily operation, then Esco isolator can be equipped with automated pressure hold test, or we call it APHT, which doesn't require any operator input. So you just need to start the test by clicking in the interface display.
Wow.
So for this test, it allows you to check if there is any problem like a degrading seal, unsecure gloves, or potential leaks before it becomes a complete failure.
Okay.
And you can also show auditors continuous record that proves your containment is always working within safe limits.
All right. Okay, that's actually good that we have it here in Esco. All right, so we have a few types of compounding isolators here, such as the SCI and HPI. So can you tell us what is the difference between these two models?
Okay, so the key difference of those two units lie in their air quality and leak tightness. A streamlined compounding isolator, or SCI, provides ISO class 5 air quality, which is the standard for a sterile environment. In contrast, a healthcare platform isolator, or HPI, offers a higher level of air quality at ISO class 3.
Mhm.
It means the air inside HPI is more cleaner with fewer particles. And moreover, the HPI is tested to a stricter containment requirement, less than 0.25% volume loss per hour. That makes HPI more reliable for containment application.
All right, okay. Now, how about if say you would like to decontaminate, can we do that?
Yeah, for SLC RABS, SCI, and HPI, we can manually wipe down the surface of the chamber with cleaning agents such as 70% isopropyl alcohol, phenolic compounds, and also quaternary ammonium compounds. So these chemicals are able to prevent cross-contamination inside the surface of the isolator.
Okay, but how about, is there like the contamination system inside the isolator so that the operators don't have to do it like manually?
Okay, so we have a biofab system for several isolator, and which apply atomized hydrogen peroxide or H2O2 inside the chamber. In the form of fine drops, H2O2 can reach every surface of the isolator internal chamber. The isolator will control the amount of H2O2 and also the contact time. This system can allow to achieve up to 6 log reduction, meaning it can reduce the microbial load by a factor of 1 million. Yeah, this significantly lowers the risk of contamination and provides a high level of sterility assurance, which is critical when we are working with a sensitive application like a cell or gene therapy, right? But unfortunately, for compounding isolator like SEI, SCI3, or HPI are not able to perform this feature because the system requires an automation process with human-machine interface and programmable logic control or HMI PLC. If this feature is still required, we can offer a containment barrier isolator unidirectional or CBIU, which can accommodate biofab integration.
All right. Okay. So now that you mentioned CBIU, can you tell us the other features of this unit that makes it actually a perfect, compounding isolator?
Okay. The standard CBIU has similar features with HPI, but it's more complete. It can be added with APHT and biofab that we previously talked, and has been integrated with HMI PLC. In the compounding isolator that we talked before, they only have simple microprocessor-based controller. It means the client can check airflow velocity, pressure monitoring, and also alarm for the unit through the controller. The CBIU is fully managed and monitored by a PLC, accessible through an HMI. This setup makes the isolator straightforward to operate and allows monitoring and recording of key parameters. For full regulatory compliance, especially with the data integrity requirements, these records can be integrated into higher level systems such as SCADA or MES.
All right, those are actually great features of a compounding isolator. Okay, so maybe let's move on to my last question. And my last question has something to do with the tangible return when it comes to investment. So, for example, there are, director in a pharmaceutical industry or maybe businessman, and they're planning on getting, compounding isolators. Beyond the obvious safety boost, which we just talked about, can you tell us why investing in isolators is actually good?
Okay, so investing in isolator may require significant upfront costs, but if you look at the long run, they act as a powerful form of risk mitigation, preventing accident, avoiding costly facility shutdown, and also reducing the risk of legal consequences.
Mm-hmm.
Beyond compliance, Isolator ensure consistent product quality while safeguarding both operators and the environment, which are critical in the pharmaceutical compounding.
Mm-hmm.
By adopting Isolator technology, we demonstrate that our institution is committed to patient safety, regulatory standard, and also institutional credibility.
All right, so thank you very much. It's actually a very good answer. So thank you for sharing your knowledge and your expertise on compounding isolators to us. I've learned so much from you, really so much. Okay, so now we understand how compounding isolators are very important in manufacturing pharmaceutical products. It's important to protect the products, the patients, and of course, the operators. So if you want to know more about our compounding isolators here in Esco, make sure that you visit www.escolifesciences.com. And once again, this is Sheena Verhal, and this is Inside the Sciences. Thank you very much. Bye-bye.